start the recording. Okay. So today we'll be covering decidability, computability, semi-decidability, and Church's thesis, among a few smaller other topics as well. So let's start with decidability, undecidability, and computability. They all kind of lump together in one topic anyway. So what can be decidable? So a decision problem. You can think of these as a yes or no question. So is this number prime? Is this word in this set of words? A property of words, does this word contain only A's and B's? Or languages, so is this word W in the language L? So what does it actually mean to be decidable? So decidability defines whether or not a property or problem can be decided. And in this context, to be decided means that there exists a program or algorithm that consistently and correctly sorts inputs according to the problem or property. So it will always sort of match the property or language. So for example, assume we have the problem P, where P asks if two regexes are equivalent. We learned that this is decidable as there exists an algorithm to cleanly check that they are equivalent, because we can turn them into automata and then run them in parallel and then check that the accepting states actually they agree on the accepting states. So for example, assume we have a decision problem over the word sigma star. We can express decidability in two different ways. So either through a function which maps good accepted words to true and bad unaccepted words to false, or as a subset of sigma star containing only accepted words. So often we'll use the function definition for if there's, I don't know, not finitely many acceptable words. If there could be infinitely many different acceptable words, we'll use a function. Or if it's a finite number, we'll use the subset. So if we can cleanly define either one of these using an algorithm, then this problem can be decided. So if a problem or language is undecidable, it's impossible to make an algorithm that will accurately match or recognize the language. It's just the opposite of decidability. And computability is similar to decidability, except it deals with whether or not the problem can be solved by a computer. So more specifically, we care about whether the problem is Turing computable. So that means whether it can be computed by a Turing machine. So we say a problem is computable if there exists a machine M, and where for all x in the language L, M of x maps to true, where L is a language and M is a Turing machine. So now we've covered all of that. Semi-decidability is where things get a bit dicey in terms of how to define stuff. A bit more theoretical. So semi-decidability is when a language or property can be accurately decided only when a given word holds that property or is in the language, but you cannot decide if the word W is not in the language. So this is easier thought of as a computer program. So imagine we have a language L and a program P that attempts to recognize L. If this language that P is trying to recognize is semi-decidable, then we'll only be able to determine if the word W is in the language. But if the word isn't in the language, the program P will hang, which means it will just run forever. So how does this make L semi-decidable? Well, if you think about this program that's hanging forever, you can't just stop the program at an arbitrary point and be like, oh, okay, So this program's hanging because this word isn't in the language. What if we gave this program like another 5 seconds to run, and it actually returned that the word was in the language? We can't cleanly say whether the program's hanging because it's taking a long time to process the word, or if it's hanging because the word actually isn't in the language. Does that make sense to everyone? Yep. Okay, cool. So we can only be sure that a word holds the property. We can't say for sure that the word doesn't hold the property. So there are two relationships between semi-decidable properties and decidable properties. So one, any property that is decidable is also semi-decidable, because we can just have the program hang when it detects that the word isn't in L. Like if we have like a program that detects the language, we can just have it hang when it detects a word that isn't in the language, and we've just made like a semi-decidable machine for this program, for this problem. And if P and not P are each semi-decidable, the property P over all is decidable, because you can surely say, using the semi-decidable machine for P, that the word is in L, is in the language, and the semi-decidable machine for not P to say it's not in the language, and both of them together make a decidable machine for P. Does that also make sense to everybody? Yeah, yeah. You can just like take the machine and its negation, and then make a decidable machine for it. So Church's thesis, or the Church-Turing thesis, states that any computation using an algorithm can be done on a Turing machine, and if it cannot be done on a Turing machine, it cannot be done algorithmically. Which leads us to the halting problem. So the halting problem is an example of an undecidable problem, one that cannot be solved algorithmically. So now we understand all the prerequisites, we can understand what the halting problem is. So assume we have a program P that either halts or hangs. So it either stops at a certain point or it goes on forever. The halting problem states that it's impossible to make an algorithm that takes a program and its input and returns whether or not that program will hang or halt based on that input. So like that's great and all, but how do we prove this? How do we know that it's undecidable? How do we know that there is no there's no program that can actually solve the halting problem? Well, that leads us to our proof. Let's start. Okay, so let's start the proof by assuming the opposite of what we are trying to prove. We're going to do this by contradiction. So assume that the halting problem is decidable, and there exists a program called H that takes two inputs. So A is a program, and B the input of A. So it inputs into A, and the overall program H returns true if A halts with input B and false if it hangs. So it sort of asks like this. So it takes in A, takes in B, and says, will the program A halt with input B? Yes or no? The exact details of how this halting program works isn't really relevant. We're just assuming that this does this, like that it can tell. So next, let's modify H slightly. We make it loop forever if it ever returns true, and we can call this new version H plus. So on its own, the machine H plus seems like quite benign and random. Like, why did we make it loop forever? But it will all make sense on this next step. So what happens if we feed H plus into itself as its own input? So will the program H plus halt with the input H plus? So we can see we reach a problem here because if h plus the input, this part, halts with this with this, then h plus the output here hangs. But if it hangs here, it halts here, which is a contradiction. It halts when it hangs and it hangs when it halts. So since that's a contradiction, we can say that the program H simply cannot exist and the halting problem is actually undecidable. Does that make sense for everyone as well? Uh-oh. Uh, can everybody hear me? Am I lagging? What was the last bit you guys got? It might be me. Sorry. Oh, okay. Right. Does everybody understand the proof? Do you want me to go back? I can go back and like re-explain it. So the is H plus. So H plus is the actual machine. How do we feed that in as an input? So what I mean by this is we make like a duplicate program of itself and put it into like H plus and um use it as its own input for itself. So will the machine that detects whether or not a program hangs hang or not? And then if it's true, then that means that this program halted, but that means it hung, which doesn't really make sense. They did it in a different way on the slides, but I didn't really like how they did it. Does that kind of make sense? So when we're passing the program H plus and the input H plus is the input of the machine, the result of running the program H plus. Yeah, it's the result of running the program H plus on another instance of H plus. And so if that input hangs, the overall big output is that it halts. And if the input is that it halts, the output is that it hangs, which doesn't really make any sense. Like I said, it's a contradiction, which means that the halting machine cannot exist. Yeah, okay. So to be fair, I kind of like breezed through it. Okay. Next, I mean, we didn't really, it's not really in the title, but there are a few others that weren't in the title that I feel like we should know, because there aren't actually any more theories of computation sessions. So undecidability by reduction kind of like relates to the halting problem. So in my last session, I explained what a reduction was in detail, but for the intents and purposes of this session, you only need to understand that a reduction is a function that maps one problem to another. If you can solve one, you can solve the other. So here I will refer to A as the problem that's being reduced, and B is a problem that A is being reduced to. And so all a reduction really says is that an instance of problem A can be seen as an instance of problem B. So if you have a problem A, you can sort of like translate it into like a problem B. So if B is the halting problem though, we can also say that A is also undecidable, since B is undecidable. And we can see that like the opposite is also like true. If B is decidable, then A must also be decidable, because if you can translate like, I don't know, like a semi-decidable property to a decidable property, you can just translate it back into a decidable form. Does that make sense to everyone? Yeah. So to prove A is undecidable, we want to reduce A to the halting problem. So if you can reduce A to the halting problem, you're kind of saying that this problem A can be seen as the halting problem. And because that can happen, that means that if you could get a solution for B, the halting problem, you could get a solution for A. But we know that, and we've proved literally right here that having a program that recognizes whether something halts or hangs is impossible. So getting a solution for A must also be impossible. Yeah. Um, so now we'll move on to semantic and non-semantic properties. So a semantic property is a property relating to the output of a program. We don't really care about the body of the code. We just care about what it outputs in terms of like semantic properties. So consider the two following Java methods. So we have A and B. So A and B are semantically identical. They have the same output. They'll both print hello to the output, but A and B are not identical because B has like an extra comment that isn't present in A. So they're not identical, but they're semantically identical. So when it comes to if semantic properties are decidable, there are three types of semantic properties. Some of these feel a bit like stupid and like, why do we need to? It's pretty obvious, but just bear with me. So a semantic property that never holds is decidable because we know that that property will never hold. So we can decide whether or not it holds. And the same with a property that always holds. But number three, a semantic property that may hold in some cases, but fails to hold in others is undecidable. And number three is known as Rice's theorem. So we'll move on to a proof of this. And so to prove Rice's theorem, we have to start with a property that sometimes holds and sometimes doesn't. We call these properties non-trivial. So let's call our non-trivial property P. The property P is held by programs that only print some form of A's and B's in a some form of like A's in a row or nothing. So first, let's make a nullary program that, okay, we'll call it F, and it holds P if it only prints some number of A's. So the body of F would look something like this. So inside F, there's another function, H, and it takes an input of A, and then prints out something that would make it not hold that property. So what is H though? So H is another program that may halt or hang depending on what the input of A is. So since it could halt and it could hang, and we've kind of like reduced this semantic problem to the halting problem. And since we can do that, we know that it's undecidable. So more specifically, we can see here that if H of A, if that halts, it will print out something that doesn't hold the property. But if it hangs, it won't print out anything, and F will hold the property. So we can say that we've reduced this problem to the halting problem. And since we know that so this creates like two prerequisites for making a semantic problem undecidable. So it has to be semantic, first of all, and it has to be non-trivial. And if those two things hold, the semantic property is undecidable. Sorry, I fumbled my words there a little bit, but did that make sense to everyone? Go back one slide for a second. Sure. To this. Right, so that's actually all of the content I wanted to go through. Um, Before I move on to like a few, you can leave if you don't want to do some like practice questions. But to be fair, they're quite easy. Does anyone have any questions before I move on? Okay, I'll take that as a no. Right, okay. So a language A, which is a subset of sigma star, is undecidable when blank. If it's not decidable, then by Church's thesis, we also know. Do you guys want me to walk through this, or should I let you guys work through it? So a language A, which is a subset of sigma star, is decidable when there exists a Turing machine that tells you if a word W is in the language sigma star. Okay, yeah, that's good. If it's not decidable, then by Church's thesis, a Turing machine does not exist that tells you if a word is in the language or not. Okay, yeah, that's good. But more specifically, I think they wanted us to mention that it cannot be done algorithmically. Um, so what about this question? So ambiguity of a context-free grammar over sigma is an undecidable property. This means, whatever it means. So by Church's thesis, this implies. Do you guys want to work through this too? It's pretty much the same answer, really. So, so no Turing machine decides it, and it cannot be solved algorithmically. Yeah, good. So I kind of wanted to make like a poll for this one. So assume we have a property P, and program F holds P if f of six, f of five, f of six, and f of seven all return even numbers. So is P semantic and decidable, semantic and undecidable, non-semantic and decidable, or non-semantic and undecidable? Okay, let me. Shay, could you make one of those cool poll things? Huh? Yeah, my bad. My Discord decided to reload itself. Can can we all see that? Yeah, okay, cool. Well, there's 0 votes, so I just assume you guys want me to go through it right now. So the answer is P is 2, semantic and undecidable. We know this as returning an even number is related to the output of F. Um, so we care about what it returns, which makes it a semantic property. And we also know that it's non-trivial because there's cases where um, the program F could not hold the property. So, like for example, if f of 5 returned like an odd number and the others returned even, it would have these three all would have to return even numbers for the program F to hold this property. So we can say surely that this property P is semantic and non-trivial, which makes it undecidable. Does that make sense to everyone? Yeah? Okay, good. Um, well, thanks for listening. That's that's all I wanted to go through for today. Are there any questions? If you don't want to ask questions now, feel free to like DM me, at me, whatever. It's okay. The slides will be available later, and so will the recording. So feel free to like go back and look at those. No problem, Shay. Thank you.